Okay, so first of all, thank you everybody for being here. Yes, it's true that we've been doing similar things for a long time, and curiously, for a long time, at least we weren't aware of the stuff that we were doing. It was really funny that we were working on very much related work, and but we didn't know about each other. But then I think when we found out the work that both groups were doing, I think this was helpful for both. And in fact, some of the work that I'm doing now is inspired by some of the things that I kind of felt, disappointed with some of the things that we were doing. I found some of your stuff more interesting, and the work that I'm doing now, I think, is inspiring. And I hope it will be helpful for everybody. So I'm, as Kate was saying, the scenario, the geometry in Porto is a little bit strange because the machine learning group is kind of spread through three faculties: the Faculty of Engineering, where I'm at, the Faculty of Sciences, and the Faculty of Economics, curiously. But we all work together for many years. I'm also a researcher at the lab in AI and computer science, and an external advisor for Fraunhofer. I never pronounced that name correctly. I think I'm under the impression that this is kind of like the last talk of the season for Optima.
Yes.
So what I'm doing today, at least at the beginning, hopefully not at the end, is to show you that everything you've been doing in machine learning is wrong in terms of research, which is a nice thought for you to take home on holidays and get depressed about it. But I hopefully will show that there are some opportunities. And I'll give you this. Well, my perspective is on what we do currently in machine learning research and what we should be doing. And my work was mostly on this thing called meta-learning. But the problem of meta-learning, is that the data that we have for the learning part of meta-learning is not enough. And I became interested in semi-synthetic data for that. But besides then understanding algorithms, which is what we do in meta-learning, I'm also interested right now in understanding models. And this is related also to this current trend of responsible AI, where we need to deliver models that people understand and understand limitations. I've actually started using the expression stress testing of models, which I then found out that you used as a stress testing of algorithms.
And models.
And also models, okay, yeah. I didn't know that.
Not too much on the modeling, but we do have a paper that's about to be accepted, I hope, in EJOR, I think, okay, on models for bin packing.
Okay, I'm really curious about that. I'm going to tell you a little bit.
In fact, I don't know why my student is not here. He's sitting out there. I'm just going to go and get him because I want him to be here. So, this is basically what I'm going to talk about. And by the way, since this is a kind of informal setting, please interrupt me anytime. I can rush through, I can remove parts of my talk if we're taking too long, so please, I want us to be interactive. Okay, so these are the conclusions of one paper that I think illustrate very well what we should do in empirical machine learning research. So the conclusion tells us that the results show that the predictive accuracy of decision trees, either pruned or both pruned and unpruned, is not sensitive to the goodness of split. So you can use multiple ways of splitting, multiple splitting criteria in decision trees. And what this paper tells us is a general conclusion about that. And this is science. So we learn something about these algorithms. Well, unfortunately, when we read papers nowadays, or we listen to talks in machine learning, this is the scenario. This is the sad scenario. At some point in the talk, you'll have a slide like this that basically shows that the method that this person is proposing, or that this group is proposing, is the best method ever. And by usually
1 percentage point, 2 percentage points if we're lucky. And if you start thinking that people are publishing tens of thousands of papers in machine learning nowadays, you know, things start getting weird. It's hard to believe that 10,000 papers in machine learning every year are proposing something which is better than everything else that was done so far. So this kind of research that we're doing simply is not what we should be doing. We don't actually learn anything, right? So this could be any paper. You've seen tables like this. What do you learn from the method that this person has presented? I think nothing, except that this person has an ego. And I should stress that my students and my papers will have this slide as well. So I'm not doing better than everybody else because my students need to get published as well, right? So I'm discussing this, but I hope that the future is not like this, but my future, my present is also like this. And you can also think about this as, you know, we old researchers, those were the days we do things correctly, but the young people these days, they are doing research all wrong. Well, if you look at this paper, actually you see that even though the way that they phrased their conclusions was very interesting, was as science should be, they drew conclusions out of 4 data sets. So they tested their methods in 4 data sets. One of them was an artificial data set. And they drew these wonderful conclusions out of 4 data sets, which obviously doesn't make any sense because you cannot draw general conclusions out of 4 sets. And this paper is a paper from 89, so it's a very old paper. So this is not a new problem, it's actually a very old problem. And how did the machine learning community react to that? I think actually the community reacted at the time very well to this. So we started creating repositories. So that's the old image of UCI. Now it has a new look. You have OpenML. There's one here. Also, you've started creating one Maxima, I think. Matilda, yes, yes. So, and there are several repositories where you can find lots of data sets, so that your papers do not have to draw conclusions based on 4 data sets. And this was actually very good. And this is a paper from 2014, I think, that became very popular at the time because they tested a huge number of algorithms on 121 data sets. So this was a very extensive experimental setup. And even though 121 data sets, it's not a lot, it's not a huge number, well, it's much better than 4. And we can start drawing conclusions. The problem with this paper is that they didn't try to understand the algorithms. The conclusion was the classifiers most likely to be the best are the random forest. That's it. Right? And again, what do you learn from this? Not much. Right? So one short detour I would like to make is that there are actually some results. I'm showing one work of mine, but there are other results indicating this, that these repositories can be overfit by researchers, in a sense that an algorithm seems to work better on those sets of data sets, on those 100 data sets, just because it was the hyperparameter tuning, for instance, was done in a way where the results, the algorithm shines much better with those 100 data sets. Back in early 2000s, we were working on a European project called Metal, which was about metalearning. And we got some new data sets that nobody had before. And C50 was at the time the algorithm that everybody was saying that was the best algorithm. And since we had data sets nobody had before, we did some experiments trying to figure out whether the performance of C5 and other algorithms was better or worse on the new data sets compared to the UCI. So we didn't have that many data sets, so the conclusions are not definitive, but there was some evidence that C5 was actually overfitting UCI. It was fine-tuned to work well on UCI data sets. So again, we're better, but we're not that much better. So meta-learning was one of the ways I believed, and some of us believed, that we could do better, which was instead of just comparing our algorithms on 120 data sets, we could actually try to relate the characteristics of the data sets with the performance of the methods. So for instance, if I have all of these UCI data sets, 100 data sets, I can characterize them in terms of meta features. I think most of the people here will be familiar with this notion. Things like, for instance, number of attributes, number of classes, if it's classification, other more complex stuff, but statistics or other measures that characterize the data sets. And then if we do that, our data sets become a point in a kind of an Euclidean space like this one. So this point here, each one of these points here are data sets characterized according to some features. And once we get that, we can apply machine learning algorithms to tell us something about the relationship between the meta features and the performance. So for instance, in this case, imagine I have two algorithms, green and red, and what I was looking for are rules that tell me when red is going to work better and or when green is going to work better. We also did it, we were very enthusiastic at the time with this problem of algorithm selection. That's what we were doing, because our goal was not as much understanding the algorithms, but actually given a new problem, predicting which is the best algorithm. So this was what we were doing then, but the meta knowledge that we could extract was something that we would like to be interesting, which never ended up being, to be honest. But there was some, as part of that project, there was some interesting results. For instance, there's this paper by Alexandros Kalousis and some colleagues, even João Gama from my university, where they analyzed all the results we got as part of the meta project. And one of the simple conclusions, but still I think it's interesting that they draw, is it doesn't matter which algorithm you use when class entropy is low. So if you have a data set, class entropy is low, you can use any algorithm, it doesn't really matter. Don't waste too much time selecting. Which is, again, I think, useful knowledge, even if not terribly surprising. Here in Optima, you were doing some very interesting stuff with the instance space analysis, which was not only, well, I don't like to explain to you, if I say something silly, please forgive me, but the idea is to project those meta features into a smaller space and then visualize this idea of algorithm footprints, which is a brilliant idea, creating this algorithm footprints where you can visualize the behavior of an algorithm. So over there, if I understand, if I remember correctly, the yellow are the places where the algorithm works well, random forest in this case. The blues are where it doesn't work as well, or vice versa. I don't really remember. But you can visualize the behavior of the algorithm. And if you can interpret the axis, the y-axis and the x-axis, then you can actually interpret what are the regions. You can assign meaning to the regions of where this algorithm works better and where it doesn't. But still, let's come back to the issue of the number of data sets. 121 data sets is not that much. So we're trying to do meta learning. We're trying to apply machine learning algorithms on a meta data set. Remember, each data set represents one point in our meta learning. So we're trying to do machine learning on 120 data sets, which is definitely.
That's not a sentence from our paper, though, is it?
Sorry?
That's not a sentence from our
No,
paper.
that's from the
Because
paper.
we use OpenML as well as UCI. And maybe,
Yeah,
Yeah.
but
But
it was like 200.
yeah,
300.
it's still not a lot, yeah.
Yeah, it's
Yeah.
not that much. So one of the approaches is the use of artificial data. This is the paper for these spaces for machine learning. And basically, again, I'm hoping I'm not saying anything too silly here, is basically the data is, the new data is generated using these Gaussian mixture models, where the data is generated trying to constrain the data that is generated to have some desired meta-feature values. I think that's the basic idea. But the idea is that the data is artificial, but the characteristics of the data are the ones that we desire. But to be honest, I don't like that very much. So I've been.
I read the conclusions of the paper, it was like open challenge.
Yeah, it's one of the challenges that you say that is that, and I think the reason is this one, right? So if you think about the no free lunch theorem, this is the universe of the no free lunch theorem, the light gray area, which is obviously much bigger than the region of the real problems that we can encounter in the real world. So when I had to explain this to students, usually what I say is that, you know, the universe of all data sets contain data sets where the average age of people is 300 years old. Right? That's the universe of all data sets. But we know that we will never collect a data set where the average age of people is 300 years old, at least not in the near future. So when we generate artificial data, my guess is that we're going to generate a lot of data sets that are out here and very few that are in here, which is the area where we're interested. And we don't really know if the behavior of the algorithms in this particular area is going to be the same as in the real world. And my guess it's not.
But there is a difference between random data sets versus randomly generated data sets to achieve a certain feature value. So for instance, you might want the age feature to be, you know, within a range. That's not the same as a random unconstrained number. So I agree with your sentence, random data sets are probably not very realistic. But the previous slide was talking about a method to generate to a distribution with a required feature value, and linking the two together, all you have to do is figure out what realistic feature values are, and then you could say you are randomly generating real world like.
I have many doubts about that, to be honest, because I think the main challenge is how to generate data where the relationship between the X and the Y, if we're talking about, which is my domain, if we're talking about predictive problems, I think the main challenge is not to generate data where the distribution of the attributes is realistic.
Yeah, it's the truth. It's generating the truth for the output.
It's the relationship between, it's the phenomenon that has to be realistic. And I think that's where methods to generate artificial data are still, I'm not sure if, I was going to say failing, but I don't even know if they're failing or not, to be honest.
The big challenge is generating a realistic ground truth.
Yes.
Yeah.
We know the true schema of causality dependencies. So we just
because if you knew that to be able to generate the data, we have all this problem.
the only choice is to follow some distributions that we can arbitrarily choose.
So we can generate a realistic X,
Yes.
but we don't know what the F is to generate the corresponding Y.
Yeah.
And of course, we can do that by forcing the F, but we were discussing that I also have problems with that testing. I think there's a lot of. So my perspective is that we can try to use semi-synthetic data for that. And we can try to use semi-synthetic data to understand algorithms and to understand models. And I'm going to talk about 3 things that we're doing for generating data: manipulation, morphing, and data set audits. So the idea, so the goal, the promise of what we're hoping about semi-synthetic data is that magically, by generating semi-synthetic data, all of the data sets that we generate are here. Not only in terms of the attributes, but the relationship between the X and the Y. This is the real challenge. Well, we don't mind if some of them are out here. You know, if I generate 10,000 data sets and 100 or 200 or even 1,000 are here, but 9,000 are in here, I can live with that. That's perfectly all right. So that's why I think that with semi-synthetic data, there's a better chance we can achieve this. And one way of doing that is by data manipulation. And there's this paper that I think I also found a reference to it in one of your papers.
Yeah, this one too.
Yeah. And actually these authors, they kind of disappeared. So I think they went to industry, unfortunately, because their work was really, really interesting, but they disappeared, I think. What they did actually was a very interesting thing, was in order to ensure that the relationship between the X and the Y is realistic, what they did was to sample from existing data sets, constrained by the kind of meta feature, the values of the meta features they wanted. So it's the same thing as the previous example, but now instead of generating the data, we sample from existing data. And then my concern about the realism of the relationship between the X and the Y, you know, I relax it a little bit, even though I'm not entirely happy. I'm a little bit, I think we're a little bit better. We did something, actually, this is one of the papers that I was presenting in Brisbane last week. One of the things that we did in data manipulation has to do with understanding the behavior of label correction methods. I won't go into detail here, but basically label correction methods are very important for fairness in machine learning. And what we did was we used, so in these scenarios, what we have are data sets where we have one attribute, which is called the sensitive attribute, let's say age or gender or race or income or whatever. So there's this attribute which is sensitive. And the label is affected by this sensitive attribute. And the problem with this area is that there are maybe, I don't know, maybe less than 10 data sets for people to do their experiments. So how can we generate new data sets to do that? What we did was we took standard UCI data sets. We picked one data set, arbitrarily we said, this is the sensitive attribute. And then we gradually inserted noise in the label depending on the value of the sensitive attribute. So the data is real. The bias is artificial. We inserted bias artificially, but hopefully we're still dealing with realistic data, even though this is art. But I think it's better than generating data artificially, to be honest.
You're talking about prediction or classification?
We're doing this for the classification.
Okay, so adding noise on the label means swapping a 1 to a 0 and a 0 to a 1?
Yes.
That's quite a lot of noise. I mean, that's completely changing.
Yes, but we're doing that to simulate what would happen in reality. So for instance, imagine that a time or a company that hires men over women, who gives preference to men over women. What we're doing is, so there's this sensitive attribute, which is the gender, and then there's the label, which is hiring. What we're doing is we're picking this sensitive attribute, which is on a different data set, which is not hiring data set. And we pick one of the values of that attribute as the what's it called, the biased group, and then we change the labels according to the values of that attribute. So we're not changing it randomly, we're doing this to try to force bias concerning the value of another attribute.
Will make that variable to be strongly predictive and the rest. So,
Yes, but that's what happens in biased datasets.
So you don't know the true causality or causality patterns. So you instead of trying to see how does it learn the true patterns, you simply introduce your own patterns that you are aware of and see how it can learn your own the causality patterns.
We're not trying to see if it learns. We're trying to, because these are not good patterns. Basically, these are bad patterns. So bad patterns meaning prejudice. And what we're trying, then what we do is we apply these label correction noise methods to correct those labels. And then what we do is we add more noise and more noise and more noise. And what these pictures show is as we add more noise, what is the impact in terms of several measures on
so vice versa, you want to teach your system how to disregard this causality. Because you assume that is an appropriate bias.
Yes, it's an inappropriate bias. Yes. That's what those methods want to do. What our data generation method wants to do is to, since we only have less than 10 data sets to test those methods, we want to generate more by using standard data sets, and we introduce ourselves let's say fake bias. It's not real bias, but it's bias. And hopefully what we expect is that the behavior of the methods on these data sets will tell us something about what the behavior of these methods on new biased data sets will be.
So this noise that you introduce, is it a random or is it a function of other features that you have?
It's a function of the feature that we arbitrarily selected as the sensitive group. It's sensitive attribute. So imagine
from a group of features generally.
Yes, we pick it arbitrarily. Actually, we could. One of the things I would like to do is actually do it randomly. For say, for instance, if you have a nominal at a binary variable, what you could do is you decide, this variable will become. It doesn't matter what it is. Could be whether I have a car or I don't have a car. It doesn't matter. And what we do is we say, people with a zero value on this variable, which we now say it's the sensitive variable, are the sensitive group. And then what we do is we change the label, taking into account the value of this sensitive attribute.
This is another whole talk you gave in Brisbane earlier in the week. I think there's a bit of interest in that talk, but don't want to hold up the rest of your presentation, but maybe if there's more questions at the end, you might have some other slides. You can give us a bit more information on that approach. Yeah.
I will. So how to, some simple ways of generating semi-synthetic data. For instance, the work of Nuria, I think, was by sampling, removing data, basically. Another way, for instance, Calusis did that. You could add new data. For instance, well, not new data, but for instance, you can add random attributes to study if your algorithm is sensitive to irrelevant data or not. Or you can do things like adding noise randomly to see if your algorithm is robust to noise. I like all of these things, but I think their goal is specific. It's an important goal, but it's a specific goal. So what we're doing really here is stress testing the algorithms. Basically, we're trying to see, is this algorithm robust to noise or to irrelevant data? But still, I think this is a very important, we should do this systematically more often than we actually do. Now, the second approach we're working with is this idea of dataset morphing, again, to understand algorithms. So imagine that I have two datasets, dataset A and dataset B. We call this the source and this the target. For data set A, let's assume that algorithm A is better than algorithm B. For the source data set, sorry, for the source data set, algorithm A is better than algorithm B. For the target data set, algorithm B is better than algorithm A. So what we do is we start from the source data set and we slowly make changes to that data set. And each one of these changes will generate a new data set. And each change should generate a data set that is more similar to the target and less to the source. So basically, if you think about image morphing, where we start with a picture of a person and then it gradually transforms into the picture of somebody else, this is what we're doing, but to data sets. And hopefully, and then of course we measure the meta features of all of these data sets, we measure the performance of the algorithms on all of these data sets, and then there's one point in particular where we are interested, which is this kind of turning point. This is where algorithm A is no longer better than algorithm B, and still B is no longer better than A, or it's kind of the frontier between the two.
So you would like to have a smooth transformation between these data sets.
Yes.
It's kind of hard to guarantee that.
Very hard. So we did that with recommender systems. We assumed binary data for recommender systems. So the transformation was very easy. We take one row from this data, and we replace it with one row from this data. And by doing this, we guarantee a smooth transition. But for instance, if you think about tabular data, general tabular data, we still don't know how to do it. And that's one of the things, actually, one of the challenges I would like to.
Can I ask about that turning point? I mean, so basically, neither algorithm is better than the other. That's because the data sets filled with examples that are super hard for both or super easy for both. The performance is tied regardless of whether it's an easy problem or a hard problem. And so just as an example, you could take your classification, you could take your labels, and we know linear separability, for instance, class A, class B, right? Suppose you take your data set, which was not linearly separable, and you, over time, smooth transition, one label at a time, think, oh, if only that was class 2, not class 1, and you change the label so the data over time becomes more and more linearly separable, easier and easier and easier. So it doesn't matter what the algorithm is, it's going to get the same performance, which is 100% accuracy. In the middle there, are you referring to transformations that make the problem easier and easier and easier for all algorithms? Or are you consciously trying to make them harder and harder for the algorithm you're trying to get away from?
That's definitely a very good point, something I would like to do, but we're currently using very, very simple transformations. So for instance, for recommender systems, it's basically taking one line from here, selected randomly, and replacing with one line from this one, selected randomly.
Okay.
So this area might be an area where, as you say, the examples are all very different for both, are very easy, or half of the examples are very easy for one and very hard for the other, and vice versa.
Yeah. On average, the performance is the same. Doesn't mean it's identical for every single example, right? Yes. Yeah, I mean, we've done a lot of work over the years on evolving data sets or evolving problems that are hard or easy for a particular algorithm. But what you're talking about is evolving in a direction that makes it harder for one, but consciously easier for another, like moving in a direction. Right? Yeah. We've also done some stuff evolving instances that are discriminating. So getting away from tied performance as well, which I think is another interesting direction. Because in your middle there, turning point, it could just be a whole lot of sort of tied, non-discriminating instances that you can't learn anything from non-discriminating instances. You can only learn stuff if you have this algorithm's good on these ones and this algorithm's good on these ones. If you've got a bunch of instances where everyone's good, you don't want that for meta learning, right? So yeah.
Well, if you want to make it more easy to solve, but particular algorithm, you might just filter records by the results of prediction. Yes.
Yeah, but we've been doing this in a blind way. We're doing this randomly, but definitely one of the things I would like to do is do this in a more guided way. Also, one important thing is that we can actually do this many different times. We can have multiple trajectories from one data set to the other, and hopefully that will get us a lot of more information here and a lot more information there. And this will help us learn better about more about the algorithm.
And when you say a data set, I assume you're referring to a single classification data set with observations. You're not referring to a collection of, you're not referring to UCI repository as a data
This
set.
is a single data set.
Yeah. Okay.
And basically what we're doing, if you look at the picture that we had there, we're trying to do this, right? So we have this data set where A is better than B. We have this data set where B is better than A. We're kind of going this way. But we're not guaranteed, you know, I'm assuming here, I did this drawing, right? So I'm assuming that everything is going through here, but you could actually be very unlucky and things, you know, could go very strange.
This reminds me a bit of a different paper. So in continuous optimization, you may have a function, you know, two benchmark functions, and what they did was just a weighted sum between the two of them. You know, where at one point this one is 100%, the other one is 0, and by variating that percentage, they just made. So you could consider a data set in a way as a function. You know, that is underneath a function, and it's just the data set of the sample points from that function. And
Okay.
is how obviously this is a bit different, but you know, like if you consider that as to be the generating function, you know, how
So you could have, so assuming that we could have a model, a perfect model for each one of them, we could do kind of a combination of the two.
sort of, but you know, like for example, if I see it from that perspective, you know, you have this function. What you're doing is replacing one point in that function between them, instead of, for example, let's say there is a, I don't know, this weighted sum between these two things. So it's.
You could say this is kind of a weighting, because as we change the data from one to the other, we're implicitly doing it, right? Because the data distribution that generates the source data set is gradually being affected or being replaced.
But it's also related to, I mean, like the machine learning stuff where you had the distribution parameters, right? We were basically evolving parameters that created data sets that had a certain distribution. It's similar to Kelvin's work where you've got a generator, a problem generator, not machine learning, but bin packing problems, but you've got a problem generator that has a string of parameters. And the question is, what do the parameters need to look like for it to produce data that this algorithm likes versus another set of parameters that, you know, and you can, your line there could just be a parameter changing as we move away from generating instances that this algorithm prefers to generating instances that this algorithm prefers, understanding how that parameter controls that line. It's all, I can see it all within the same framework, whether it's a function or a parameter string or something, but it's slowly changing something as you move away from what one algorithm likes to what another algorithm likes, right? So
one important assumption about that is that we cannot guarantee that this is a continuous behavior.
Yeah, and phase transitions and things, you can get some discontinuities in that space.
And in optimization, I think that's very often the case.
I think that's what you're looking at when you say turning point. I read that as phase transition boundary, right? As we change some parameter, the performance of an algorithm might get worse and worse and worse, or better and better and better. And then there might be a discontinuity where suddenly it's terrible because the problem characteristics, like the density of the graph, suddenly dropped below 0.45, and now this algorithm is hopeless.
But here it doesn't have. Here it can be gradual. It doesn't have to be a discontinuity. Because actually, one of the things that we haven't dealt with is that for a lot of these points here in the center, you might actually not be able to say that algorithm A is better than B or B better than A. So it's a more continuous in this case.
It also reminds me of an experiment that we did some time ago, and it was just simply taking a function and just move it one step at a time across the space. And it just because this was box constrained, you could see certain areas of the function when the optimum was in a given point, and when you move it, you kind of lose that. And what that generated for someone is a complete change of the characteristics because you were basically extracting details from the function. So it just these phase transitions can happen because of multiple factors, at least from my experience, like and the structure of the problem can like definitely be very binary. Is a moment here and then.
I can think about an example very easily in machine learning. This is for recommender systems. We were using simple recommender systems, but imagine we're doing this for tabular data. If you're analyzing the behavior of a decision tree, if we add one point and suddenly the root node of the decision tree changes, then you have a discontinuity.
Yeah.
Here in this case of recommender systems, I think we were using mostly nearest neighbor based algorithms. So I don't expect that discontinuity to be so strong.
Doesn't necessarily create a discontinuity though. It's just created a different tree. Depending on how you're measuring success and color coding which algorithm is better, it may still be a similar accuracy. It's just an alternative tree. But I can see what you mean. It's created an impact in terms of learning. We better let you move on, but just note your data set morphing idea has generated a lot of interest and its relationship to evolving data sets and various things. We can talk more about that.
Do you have instances that you couldn't improve with this transformation?
Sorry?
Do you have any instances that you couldn't improve by this transformation from the original instances?
Where we couldn't find a way from source to target.
Yeah, for example,
good
making
question. I don't have an answer to that. That's a very good point. So is it possible to make the changes?
You know, the
No,
changes-
in this case of recommender systems with binary data, I don't think so.
Depends what the algorithms are, right? If your source is a great
Yes.
algorithm and your target is a terrible algorithm, there's nothing you can do to the data set that's going to make the terrible algorithm perform better than the original algorithm. And the best you can do is a tie by making it a super simple problem.
Yeah, well, if I would take optimization, like for example, NetTech problem, it's known that, for example, uncorrelated instances, they're super easy to solve. Bounded, strong uncorrelated instances, they are harder. I can set them. If I will try to introduce noise, it's very likely I will tend to make uncorrelated instances. So I would rather make it easier problem rather than a harder problem.
Yeah.
So, and in this case, my point is like why we should modify if I can theoretically, more or less theoretically set the instances to make them harder, generally for all the solvers.
The problem here is that
Combo will still dominate.
yeah, the problem here is that we don't know how to make them harder because, as you see, the only way I can assure that the algorithm, the data set that I generate is better for algorithm B is by copying data from B to A, from the target to the source.
Well, we also measure based on performance of different heuristics, I guess, right? Or different algorithms.
There's one more comment on knapsack. Your highly correlated instance, even those, you take one weight or probably one weight is easiest off one of your objects, you can turn an instance which is very easy into a very hard instance or vice versa, right?
Yes, potentially, but my question is, if we already have a hard instance that we model based on, well, theoretical things, right? So doesn't mean that we can construct even a harder instance by manipulating with a transformation and other things.
You'd at least have to think very carefully about the transformation.
Yes.
Who's going to move on?
Yeah, we'll
Run
run
out.
off.
I think I'm almost done also. So just show we've been doing, I think the example in time series is even simpler to understand. This is some work that we just started. We've submitted it recently. And for time series, for instance, this is a time series where an algorithm works well. I think this was worked by Moisés. This is a time series where an algorithm has a very good performance. And this is a time series where the same algorithm has a very bad performance. And we want to analyze, how it behaves. And we create time series by combining, by doing exactly a weighted sum of these two. This is actually it's already available on archive. And but this is something we're investing in.
And the final thing that we're working on is the idea of data setoid. So think about the classification problem. Let's go back to the issue of having 121 classification data sets to understand the behavior of algorithms. Now, this is one of those data sets, and I have 4 attributes and a target. And this is a classification problem, so the target is a nominal variable. And these 2 attributes are also nominal. So out of this data set, I can create 2 data setoids by swapping each one of these with a target. So in this first data setoid, this attribute, which was previously an attribute, is now a target, and this, which was the target, now becomes an attribute. And then we do the same thing for the other. And what we do here, we call them data setoids because they are real data, so guaranteed to be real data because the original data set is real data. The thing is, the target, which was originally something that made sense, so I wanted to predict if somebody is going to buy a product or not. This is something that makes sense, knowing if this person lives in some city. And now what I'm trying to do is to predict which city a person lives in, given that the person has bought a product, which doesn't make sense. On the other hand, the way we feel about this is the relationship between the X and the Y probably doesn't make sense, but it's a realistic one. I'm not forcing a linear relationship or any other kind of relationship. I'm just taking the world, what the world gives me.
Makes sense. I mean, it's a generalization of the sort of cross-validation accuracy concept for prediction accuracy, where you're not saying how good is my prediction of one thing. It's like how good is my ability to model relationships in this whole data set, full stop. Yeah, it's nice.
But we do it for many data sets. So currently, I wanted to show you results, but I haven't managed to finish them. I'm currently working with 1,400,000 data sets. So this is really cool. So we can actually do meta learning now, not on 120 data sets, but 1,400,000. And actually we're growing because we're doing all kinds of transformations to get things like this. And I'm really excited about this. So what we're hopefully getting is, you know, the dream, right? Getting a lot of problems in this region.
Of course, many of those data setoids you can't really call realistic if you're trying to predict something that no one would ever really try to predict.
Yeah, but the algorithms don't know what is the phenomena. The algorithms only care about the relationship between the variables. Yeah. And the relationship between all of those variables is real. Well, I'm exaggerating.
But the interest in one being the dependent attribute is not real necessarily.
Direction of causation important.
Yeah.
Well,
yeah, so what you're saying is that I'm sampling, if I look at the features, if I look at the meta features, I will get something that is definitely from here. If I look at the relationship between the X and Y, I might get something which is completely off. And I agree with that. But I do think the risk is less than in other cases. And the relationship is true. It's simply not interesting. You will never want to predict a phenomena with that, let's say, shape.
But it leads to another really fascinating question, which is if this was the real problem, I've got these attributes and I'm actually interested in predicting this thing. If for some reason that was a hard problem, but there was a data setoid version of the problem where some relationships could be more effectively learned, then maybe do that. It's almost like a remapping of the problem to something that maybe could be solved more easily. And then if there actually is a relationship, maybe you can kind of undo that to answer your original question. Like I wonder about if you do your, 5-fold recycling here to generate your data setoids, whether they're all equally difficult to learn.
No.
If there's a diversity there, then this is a really interesting question about, I've got my original problem. Is there a data setoid variant that's easier to solve that I can then learn some relationships and then kind of undo interrogate relationship. You know, machine learning, you can complicate it, you can still write down the equation and input and output. It might be a pathway to improving accuracy by tackling the data set or
The
version
simpler
that's easier.
version of the,
Yeah.
I've never saw it like this. I don't have an answer. I've never seen this project the way you're saying it. But
If you can show that there's variation in
there is,
learnability,
no, I can
and
tell
then
you.
that means for the original problem, there's an easier version of the relationships to model, and then seeing what you can do with that version to infer the original relationship and the thing you care about.
I can guarantee that there is diversity, because one of the problems with data setoids is that since a lot of the attributes in the data are highly correlated, what happens is a lot of the data sets that we generate are overly simplistic. So we realize that it's not just generating them, we'll have to do a little bit of filtering to avoid these cases where the problem is too simple.
You might randomly drop some values from your data set, like,
Yes.
and at some line you drop city, and some another
Yes.
line drop label, and so you do it randomly, and this all
Yeah,
will merge
that's-
into one step.
Well, I currently have a project where I promised 1 billion data setoids. So we're looking into many ways of doing that, and that's one of the days, which is sampling the attributes. Okay, so if I still have a couple of minutes, I will go through this because it's a completely different thing. So now the idea is semi-synthetic data for stress testing the models. So if you think about GANs or semi-synthetic data, as they are used nowadays, usually the goal is this one, right? So I have this data set, I have a small amount of labeled data, and what I want to do is densify areas around each one of the concepts, so the learning will be more robust. Well, what we're doing is and if you think about it, just to give you an example, imagine this very important problem for humanity, which is to distinguish between ones and sevens, right? We're all depending on a good solution for that. And if you do data generation for this problem, you would like to get some examples like this that look a lot like ones and some that look a lot like sevens. Well, what we're doing is different. What we want to do is, given this problem, I want to generate examples that are in the board. And the idea is that these models can be seen as documentation about this model. If somebody is going to deploy this model, they should know under which conditions the model is not going to work. So for instance, if I'm trying to solve the famous 1 versus 7 and I have a classifier, I want to generate examples for this classifier where the classifier has a hard time making decisions. So for instance, you know, some of these, you know, this one looks like a 1, but then it has this thing over here. So I want to generate problems basically where the classifier is not confident. If we're generating scores, we would like scores, data for which this classifier has score of 0.5. And that's it. I'm not going into more details.
How will you determine the ground truth of those? So
I
one
don't
thing
care.
is one thing to say, here is some data where the classifier is confused. That's all. That's end of story. You're happy. I've now got some ambiguous data. You're not then going to attempt to label that as. Okay.
No, that's I think the thing that I'm enthusiastic about is that we're because we're generating data like this, and then we're trying to extract patterns. So the idea is, if you have a model card that goes, when you sell this model C to a company or to the government or whatever, there should be a model card together with this model. And you can add in this model card, if the data looks like this, then don't use the model.
because the model will make
We're on the same page in terms of the warning label we want to attach to algorithms. I want to use instance-based analysis to describe the terms and conditions under which this algorithm will work well. You're going further, not just describing terms and conditions, but giving examples of where it might not.
yes.
Where actually, if your data looks like this, don't trust me.
Yeah.
Okay, nice.
Okay, and this is basically it. I just wanted to give you some idea of we're doing stress testing algorithms for label correction methods, for time series forecasting and anomaly detection, hierarchical time series forecasting, so the work that I showed you earlier. For dataset morphing, we're doing with time series forecasting and recommended systems. For datasetoids, we're doing classification, regression, and graphs. For stress testing models, we're doing computer vision, natural language processing, time series forecasting, and by the way, stress testing models in time series forecasting is a really interesting idea. It's amazing the amount of challenges we came up with. And also for hierarchical time series forecasting. And these are the two projects that I've funded my work right now, the Center for Responsible AI, which is a national project in Portugal. And in Porto, I'm responsible for it. And the other one is an European project that I think some people, Vincent and somebody else mentioned, was this is an European project where the goal, well, the motivation is we have medical data all over Europe in different places, right? And there's this general idea that if we were able to share this, to share and join this data, we would get better models for health. But the problem is, of course, privacy of the people.
The identification.
Yes. And so what the goal is to generate data sets which are very realistic, so they have the similar properties, and similar properties might have many meanings that can be shared. There should be a joint data space in Europe for health. That's what we're building, and we could put the data there and people would share it. And we're using GANs for that, but we're going to try different things. And so thank you very much.
All right, thank you.